So welcome. So this is our second video on gravity, and we're going to start talking about some of the interesting aspects of ocean tides. So this, if you like, is applied gravity. And as a physics person, I find this quite interesting because I never thought about some of these things in quite this way. So I'm going to come down here and get a pen, hopefully. My eyes are bad today. Let me just see if I can. There we go. Oh, I know why. I got my tablet upside down, so up is down and down is up. Let's try that again. Good. Yeah, good. Okay. Let's go back a couple of slides. Ocean tides. So, ocean tides have something to do with the moon, yeah? They've also got something to do with the sun. And so it seems a bit complicated. The ocean tide is when the tide rises and falls. If you go to the coast, tide rises and falls. Frankly, depending on where you live, ocean tides are a big deal or they're not a big deal. In the north of England, ocean tides, they vary throughout the year, but ocean tide, I've seen ocean tides of 15 feet easily. I've been to a harbour where the boats were floating at the side of the quay, and then I've gone back, you know, at the end of the day, and the boats have been laid on their side on mud. And that depends upon, to some extent, your latitude and also the geography of the coastline. There's a place in Nova Scotia where the tides are 56 feet, up to 56 feet. So that's just phenomenal. And yeah, if you go to the coast here, what is it, 3 feet, 4 feet, maybe 5 feet. So not such a big deal here. But most places there's two tides, two high tides, two low tides. I actually lived on a river where the tide on that estuary was so strong that it would send a wave, a shock wave, back up the river. So you would see a wave going the wrong way, going upstream rather than downstream, and traveled quite quickly and was very distinct. It was clearly there. And that represented a time when the flow of the tide in overwhelmed the flow of the river down. And as the two forces met, there was this wave. And in fact, there's even, if you go online, there's even some videos where people take surfboards, not on the river I was on, but people on some of the other rivers, because it happens throughout the world. They will actually surf up a river on a surfboard riding this wave, which is kind of interesting. Okay. So tides are kind of interesting, and where do they come from? They come clearly to do with gravity, and they're to do with gravity between the Earth and the Moon. Primarily, when you look at the timing of them, when you look at the pattern of them, they've got more to do with the Moon than they have with the Sun, but the Sun does have an effect. So they're to do with both. So what on earth is going on? What's going on, basically, is that if we think back about our force equation, we say force is equal to this constant times the mass of the Earth, and let's say the mass of the Moon, and the distance between the two squared. Here's the interesting thing. The distance from the Moon to the near side of the Earth is slightly, but significantly, it does count. It's not that it doesn't count, but it's only slightly different between the separation. So the distance from the Moon to the near side is slightly less than the distance between the Moon and the far side. And that means that the R is slightly less for the near side pull of gravity and slightly more for the far side pull of gravity. And even though the mass of the Earth is the mass of the Earth in both cases, and even though the mass of the Moon is the mass of the Moon in both cases, and even though G is the same in both cases, these two differences in the distance matter. And so what you find is that there's a bigger pull of gravity on the near side of the Earth than there is on the far side of the Earth. So if you imagine taking a hula hoop, you guys know what a hula hoop is? They still have them around. You know, you put them around your waist and you spin. And if you imagine a hula hoop, and it's hard to pull more on one side than on the other because you're pulling on both sides, so you're going to accelerate in one direction. But if you cheat and you hold the far side still and you pull on the near side, what happens to the shape of the hula hoop? It gets oval, doesn't it? It becomes like an ellipse. And so what you find is that the circle becomes an oval or an ellipse. And that literally happens to the earth. Literally. The earth is elongated by this pull in the axis that is in line with where the moon is. And it's measurable, and it affects land and ocean. So this building rises and falls by something like 22 centimeters twice a day. It's not unmeasurable. We don't notice it because everything rises and falls. But in a way, it's like we're taking a metal and we're just twisting it backwards and forwards and backwards and forwards. If you took a spoon and you bent it backwards and forwards, it would get hot. Yeah? Just that work would make it hot. The moon's doing the same thing to the earth, and that is actually partly what drives our earthquakes and the like. That's putting energy into the earth, and it's flexing the earth's crust. And because of that, because the position of flexing keeps changing, at one point we are high, but California is still low. And then a little bit later we start coming down, but Texas is high. And a bit later we've come down further and California is high, and so on. This constantly massaging of the Earth's crust causes some energy to put in, and it also causes some instability, which triggers, in some cases, earthquakes and the like. So, yes?
Why is it that some areas have more earthquakes?
Oh, because the crust is kind of made of plates. And so although we're flexing our crust, we're not where two plates are going to rub together. So you see the bigger effects where you're on the edge of a plate. Although there are some situations where in the middle, the very middle of a plate, you will get some activity. Like Hawaii is not on the edge of a plate, it's on the middle of a plate. So you get these hot spots where stuff is happening. But most of the observable stuff happens where the plates kind of rub against each other. But in part they're rubbing against each other, not the only mechanism, but in part they're rubbing against each other because of this system. I'm getting over into geology. I'm feeling less and less comfortable, but you know. But so okay, that's with land. What about with water? Water can flow. And so what we find is if you're in the middle of an ocean, you find that the water level, if you could measure using GPS your altitude compared with the middle of the earth, you would find that your water level would rise and fall by about 1 meter, 3 feet up and down during this process. You're literally pulling a bulge of water towards where the moon is, and it's like holding that bulge of water as the earth spins. Now think of it as, don't think of it as the moon spinning, think of it as the earth spinning underneath it. So the water gets held by the moon and the earth spins underneath it. So we're pulling this bulge of water. Why is there a bulge on the far side of the earth? And the only thing I can say is symmetry. It's kind of like if you pull one way, the forces, the elongated oval means that if there's a bulge on that side, there's going to be a bulge on that side. It's a very weak explanation of it, you know, but it's you know, that's as good as I can do. So we say, remember the inverse square law, the gravitational pull of the moon is greater on the near side of the earth than it is on the far side of the earth. This is like tugging on a ring at one point. The ring elongates into an oval. There's a similar but much smaller effect caused by the sun. Now the sun is also distant but much, much further. So imagine taking the size of the earth, the diameter of the earth compared with the distance of the moon, and the diameter of the earth compared with the distance of the sun. And there's no comparison. The diameter of the earth compared with the distance of the sun is, again, measurable. It is significant, but it's tiny difference. So for the sun, the two forces are much more even. Now remember, The sun is pulling harder than the moon is. This is not the moon's pulling harder than the sun. This is that the moon is pulling differently to a greater degree than the sun is. The sun is pulling very hard, but virtually the same force. The moon is pulling less hard, but quite different forces. And so it's one of these differential effects. Okay, so we're going to get a pattern. Sometimes the sun and the moon will gang up and make an even higher high tide. But other times the sun and the moon will fight each other and diminish the high tide. And so we notice these things. So for instance, when we have a situation in space where we have the Earth and we have the moon and then we have the sun, then the differential pull of the moon is quite big. And there's also a little bit of a differential pull of the sun, which is adding to it. So this will be a very high high tide and a very low low tide. And actually, it doesn't matter which side the moon is on. It can be on the opposite side to the sun or on the near side to the sun. We're going to get the same effect. And so we call these things spring tides. So the first little problem is spring tides don't happen only in spring. Spring tides happen whenever the sun, the earth, and the moon line up. And this happens, well, this happens at a new moon. And we don't tend to see new moons unless we look for them. Sometimes if you're driving home after an afternoon class, you might see a slither of the moon like on the horizon. And that's because it's almost a full moon, almost a new moon. The new moon is when really the moon is very close to the direction of the sun. And we just can't see it among the blue light caused by the atmosphere. We don't notice the moon. The moon is largely in shadow. The face of the moon that we see is largely in shadow. So it's not emitting a lot of light. And the blue haze caused by the atmosphere just drowns out what we can see for the most part. When the perfect alignment takes place, then we get a solar eclipse. And one of those is coming up this next year. There's going to be a solar eclipse. But you don't see it in many places on the Earth. So there's many times. There's once a month we will have a new moon. And the reason why they don't line up is it's not perfectly aligned. The plane that the moon moves on is slightly different from the plane that the sun moves on. So not perfectly aligned. And then the other thing is, of course, when the moon is in the Earth's shadow, or nearly, and that would be a full moon, because usually they're not aligned. So we see, like, over our head, we see the light comes from the sun overhead and makes the moon look full. So we get spring tides twice a month, typically. What happens when the moon and the sun are basically at 90 degrees to each other? Then they fight each other. So whatever maximum tide you get because of the moon, all that water is not available because 90 degrees around the Earth, the sun is causing its tidal bulge to go in that direction. And it diminishes the tidal mound caused by the moon. So they fight each other. And this would be, and if I remember my astronomy, so this is first quarter. It's when the moon looks half. On the right-hand side, it's lit up. And this is third quarter. So lots of tides, spring tides, twice a month. These are called neap tides. They're twice a month. So we line them up. So we say when the Earth, Sun and Moon line up, we get bigger than average tides, and these are called spring tides. When the Sun is at 90 degrees to the Moon, the tides are smaller than average, and we call these neap tides. And I got to be honest with you, I am simplifying the reality. Because if you look, what I'm telling you, then fine. We should have a very predictable tide, which is, as the week passes, pretty constant or diminishes quite predictably at St. Petersburg Pier. And it's not. It kind of bounces around a bit because there's other aspects involved in it. But in principle, this is what's going on. So, for instance, we can actually use our clickers. Yay, I got that to work. So which type of tide is this? Is it the spring tide? Is it the neap tide? Is it the high tide? Is it the low tide? What do you think? Okay. So what do you think? Yeah, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people. I'm going to stop there. We got pretty well everybody. I'm going to stop here, and then let's have a look and see what people say. Most people are saying A, and that is what I would say, because these are in line with each other. So this would be actually looking from Earth. This would be a new moon, which is all in line. That would be a spring tide. So that's spring tide. And then for this next one, which type of tide is this? And I think we can get it. I'll do it. It's going to be a neap tide, because if you like, the bulge that's caused by the moon is offset slightly by the bulge that's caused by the sun, and so we get one where it's kind of like it's not quite as good as it could have been. You know, it's like that. Okay, so why are there 2 high tides and 2 low tides? And the trick with this is to recognize the fact that it's the Earth that's spinning. The moon's not particularly moving. The Earth's spinning, and so there's this bulge at one side of the Earth held by the moon, and there's a bulge at the other side of the Earth that's held by the moon, and we spin once in 24 hours. So in 24 hours we go under one bulge, and we go under the other bulge. So we get 2 high tides and 2 low tides in a day. So the axis of the Earth. Oh, and why is there a high tide, and where is there a low high tide? Because it tends to be. It's not 2 high tides that are the same height. There is a difference, and that's because of the tilt of the Earth. We get 2 high tides because the Earth spins once every 24 hours, but we get a high tide and a lower high tide, because if you imagine the axis of tilt of the Earth, the axis of spinning of the Earth is not at 90 degrees to the direction that the moon is at. And so if you imagine, I've tried to show it on this diagram, that's deep water and that's not so deep water, just because of the geometry of the thing. And so I would expect a high tide and a not so high tide. And so we get this non-uniformity as the day passes, and we see that very often. So the axis of the Earth is not perpendicular to the plane holding the Earth, Sun, and the Moon. As a result, the point on the ocean experiences slightly different tide heights during the day. Let's reverse things and look at the Earth's effect on the Moon. Now, because the Moon is smaller, if I take the center of the Earth and I take the Moon effect, the distance to the near side of the Moon is slightly smaller than the distance to the far side of the Moon. Because the Moon itself is not so big, there's less of a significance. So the Moon has more significance on the Earth than the Earth has on the Moon, because the Earth's diameter is bigger than the Moon's diameter. Does that make sense? So the fraction of the Moon's diameter to that separation is less than the fraction of the Earth's diameter to that separation. So we get less of a tidal effect on the Moon. And there's also no water. So it's tempting to say there's no tidal effect. But an interesting thing happens. It turns out that because of this tidal effect, we do get an elongation of the Moon. In fact, what we get is, and this is, again, I'm having a hard time, the Moon saw. The Moon is not spinning. It's pretty well looking at the Earth all the time. And so what we tend to get, if I draw this a bit better, we tend to get this like belly effect, where the near side of the Moon is bowed like a belly, and the far side of the Moon is not so bowed. And things tend to spin on their center of mass, but the center of gravity in this case is slightly in a different position to the center of mass. So it's a bit like having a pendulum where we have an axis rotation and we have a mass that's held down in a gravity field, and so it tends to want to hang vertically down. So the moon tends to want to keep this axis pointing towards the big gravitational pull, and the big gravitational pull is the Earth. So the moon, if you like, has a belly, and if it tries to get away slightly, it gets pulled back like a pendulum. If it tries to get away slightly, it gets pulled back. And so there's a mechanism that keeps the moon's face pointing towards us. I mean, if you think about it, you can look back at paintings from, 300 years ago. And to the extent that they could draw the moon, well, the telescope, 400 years of the telescope. So Galileo was able to draw the surface of the moon really quite well. And you can look at his notebooks, and we can look at the moon pictures, and we can see nothing's changed, really. Maybe a few more craters here and there, but, the big thing's all the same. Not many more craters, to tell you the truth. It doesn't happen that often that it's noticeable. But the same face is pointing towards. And if you go back even further and have these like little drawings that people did before they used telescopes that still draw the moon, it looks remarkably the same. And if you measure the change, it's not the same. Now, there's two possibilities. One is that by chance, the rotational period of the moon's rotation is the same as its revolution period. It takes once a month to revolve. It takes once a month to rotate. What are the chances? The Earth takes once a day to rotate and once a year to revolve. They're not linked at all. There's no law that says these have to be linked unless there is a gravitational locking. And so what happens with the moon is, because it is in just the right position to a bigger object, it gets locked. The Earth is in just the right position, but to a smaller object, so it does the locking. So we say the moon is elongated because of the tidal pull of the Earth. We say the bulge on the moon stay in fixed locations. The moon takes as long to spin once as it does to revolve around the Earth. So the same face is always facing the Earth. The system is regulated by the fact that the moon's center of gravity is slightly displaced from its center of mass. Whenever the moon's long axis is not exactly lined up with the gravitational pull of the Earth, the force of gravity swings it back into line. So we see this. It's amazing. And you can look at, so now let's think about the moons of Jupiter. The moons of Jupiter, there's 4 noticeable ones. And you look at their pattern, and the one nearest is gravitationally locked and the others are not so. Sorry. The one nearest is not gravitationally locked. And that's because the ones on the outside mess with it. So the one nearest is actually incredibly active volcanically. It's like the most active place in the solar system. And the moons next to it, the ones further out, they're gravitationally locked and they're really cold. So you get these very striking differences that are explainable from thinking about the gravity. So you get this sort of these interesting effects that become noticeable. By the way, is there any place in the universe from which the Earth is not visible? Imagine the biggest telescope you can imagine. You can do whatever kind of telescope you like. Is there any place in the universe where the Earth is not visible? There's one place. Can you think of what it is? If you lived in that place, you would have never seen the Earth.
The other side of the black hole?
No. Yes, but I didn't mean that. You're right, but I didn't mean that.
The other side of the moon.
Yeah, the other side of the moon. If you think about it, it's always got its back to us. It's always got its face to us. The back to us never sees the Earth. You could live on the far side of the moon and never know the Earth was there. the only place where you wouldn't be able to see it ever. It's kind of amazing when you think about it. Yeah.
Professor, why? So why does the Earth spin around itself? Like, not like the moon?
Oh, so good question. In Earth formation, what you get, let's get my pen. So the solar system came out of a falling cloud of gas and dust. And in principle, if it was perfectly symmetrical, it would have formed a big glob of matter. And then it would have, become a star or a sun and done stuff, yeah? But you've got to ask yourself, what are the chances of perfection? And they're never there. So then you've got to say, well, that means that there's got to be some asymmetry. There's got to be something, it's not equivalent. So that means, well, pick a direction. Okay, I'm going to say it's slightly more matter on the left-hand side than the right-hand side. So then that means that it starts falling like that. And as soon as you get that asymmetry, it gets worse and worse and worse. And so you naturally, when things are just coalescing like that, you get these rotation effects. So the solar system has a rotation effect, and we see it with all the planets. And then when you form globs of stuff out of that rotation effect, out of that rotating mass of dust, the things you form tend to have a rotation on it. Now, that implies that everything in the solar system will rotate with the same sense, the same, if you look from above, clockwise or counterclockwise. And they do, apart from, I think it's Mercury does not. Mercury goes the other way. And there's a big why. And this to my mind is, I love physics. Physics takes a complicated world and it makes it complicated. And it makes it simple. Bit of a Freudian slip there. But physics takes a complicated universe and it makes it simple. But you know what? The complexity is often the most interesting thing. And so things like astronomy are kind of great because you get to apply basic physics, and depending on your comfort with the basic physics, you can explain a lot of complicated stuff in the universe. So whereas in Aristotle's day, he could just describe what he saw because he had no underlying physics. Now, with underlying physics, we can look at complicated stuff and say, this is what's going on. And that actually, incidentally, is why to become a doctor, you need to pass, to get into medical school, you need to pass the MCAT exam. And so for a while, for a couple of summers, the medical school at USF was running a MCAT training program, and they asked me if I'd teach the physics bit. And I was a bit surprised about the bit of physics bit on the MCAT. And I was really surprised when I saw the questions, because the questions were like really hard. And the first time I did them, I was like, I can't do this. I'm the teacher and I can't do this. I better get sorted out real quick. And then I sat down and started studying how you do the MCAT. And they deliberately pick areas of physics or engineering which are obscure because they want to see how well you apply basic physics to them. So on one of them, they were talking about the sails on a sailboat. And they give you this written passage, and then they give you questions. And some of the questions, of the 11 questions, I'd say 2 or 3 of them were physics. I knew the answer because I knew the physics. I knew the physics of forces, straight out of there. And then another 3 of them were reading and understanding what the chapter was about. And another 3 of them were basically applying knowledge of graphs and stuff like that. They tend to have a written passage, a diagram, and a graph. And so you know your physics, so you get 3 of them. You can read and get the vocabulary and figure out what's going on. You get another 3. And then your graph, you know about graphs, you can get the third 3. And so I was really curious about why do they do this? This is like crazy. And they said they want to be able to follow people's ability to apply physics understanding to unusual circumstances because that's what doctors do. I mean, somebody comes into your office and it's not just physics, but it's that logic. Someone comes in and they're presenting all these conditions, and you got to figure out, not remember, you got to figure out what's going on. And so they're very keen so in a letter that my old department got from the medical school, they said what their opinion, what really counts for making a good quality, the telltale for a good quality doctor in the end will be a good physical thinking, good physical science thinking. So it's kind of fascinating. So I find stuff like this from a personal point of view. I find astronomy fascinating. The other one they did was they had a resistor network which emulates muscles in the body and how the signal goes along and causes the muscle to work. And I just was amazed about that. At USF, they have a course, Biomedical Physics 1 and 2, which is designed for people. After they do 2053 and 2054, after they do the algebra-based physics, they do this as a minor in physics. And it's very popular. They have hundreds of people doing that every semester. And it really helps them, I think, as far as preparation for MCAT, because they go back and do all the physics again, but applied to the biomedical systems. So and they tend to get, there's a couple of teachers who do that. I know both of them. I know two of them. There might be more now. And they're both really very keen on it, and they do a really good job. So this next bit, sorry, I'm going off track. It doesn't matter. So this next bit is gravitational fields. Fields are very abstract. It's this idea that I can draw arrows that point in the direction that a boulder would move. So if the boulder falls from a great height towards the middle of the earth, draw the arrow in that direction. And I think you've seen it on weather charts. If you look on some of the NOAA weather charts, they have kind of like, these lines like that, and then they'll have a front, and they'll have, symbols, and these are showing wind directions. It's analogous to that. It's kind of like, it's the same kind of idea. Okay, so with gravity, things always point towards the center of mass, or center of gravity, actually, so you point your arrows towards the center of gravity. And we say, gravitational field, the Earth interacts with the moon, but there is no physical contact. The Earth interacts with the gravitational field of the moon. We can actually imagine, so here's my Earth, and here's my moon, and there's arrows coming in from here like that. But where do these arrows start? Well, you know what? They kind of come in, well, you might think they go like this forever, but this moon is going to cause some kind of bending of these gravitational field lines. And so this object is in that object's gravitational field and vice versa. So we can get these interesting diagrams. The moon interacts with the gravitational field of the Earth. The gravitational field on a sample. A gravitational field is an example of a force field, and we have electrostatic force fields, magnetic force fields, we have gravitational force fields, we have a ton of force fields. The pattern of the Earth's gravitational field lines can be represented by field lines. So here's our field lines. The strength of the Earth's gravitational field lines depends upon local geography, which is very interesting. Yes, it points towards the middle of the Earth, but what's between you and the middle of the Earth? Is it nice and uniform, or is there a big cavity in there? That's got less mass. All this mass is missing. So that's got to affect the pull of the Earth's gravity, because there's less between you and the center of the Earth now. So the pull of gravity has to be a bit less. So we can detect subterranean pockets of natural gas because the Earth's gravitational field is reduced in that locality. And so I didn't know this, but one of the things that geologists use is they use a very sophisticated pendulum system. And they go to different locations on the Earth, and depending upon the pull of the Earth underneath, they get different values for little g, the pull of gravity. And so they can infer things. I mean, remember the problem that geologists have is that it's very expensive to dig a hole, and you're effectively destroying that bit of the planet. So you don't want to dig holes when there's no need. And you don't want to dig a hole when there's, no need because it's expensive. So anything they can do to kind of predict what's underneath is really valuable. And so they use geological features like salt domes and the like were always used as an indicator of maybe there was an oil field underneath. So they dig a puncture hole in every salt dome and they found that their success rate was abysmal and has got worse ever since they started looking. The distance they have to drill and their success rate gets worse and worse because all the easy stuff got found. Now they're left with the difficult stuff. So oil exploration is really expensive. And they're always looking, so rather than digging and saying, oh, look, there's nothing there, what they then started doing was seismology, where they'd basically put a whole bunch of explosives and explode, and then a whole bunch of listening devices and listen for the shock waves, like an ultrasound. Like going to the doctors and getting an ultrasound, but they do it for the Earth. And if there's some kind of feature there that is significant, it will show up. So then they can get, if you like, an ultrasound of the inside of the Earth. But even then they're guessing. But they put that with, the geological features they can see, and they use satellites. They started measuring these Earth's gravitational field. Anything they can do to help. My wife lived in France for a year. And actually Belgium for a year and France for 2/3 of a year. If you get a chance to do junior year abroad, or you get a chance to do like a summer studying abroad thing, I really recommend it, because I didn't, and I was 25 before I bothered to leave England and go to Italy, and was stunned. I thought Italian people just were like me, but spoke Italian, so who cares? And I went there and found, people with different view on life, and they're same, but they're different, The culture's different. They're people, they're just like me, but the culture's different. And I was stunned when I went. And I came to America, and it was like similar. It was a weird feeling where it's like Britain, but it's not like Britain. And in big ways and little ways. So it's really valid. So my wife was in Europe for a long time. She spent more time in Europe on the mainland than I ever did, which is kind of ironic. And she told me this story about when she was in France, there was this scandal. And what it was this inventor had developed a black box system that could be used to detect oil fields with high precision. And you could even put it in a plane and it would detect the oil field. And so in France, there was a fair amount at that time. The petroleum industry was nationalized, so there was a national company. There were also other companies, but there was a national company. And they basically said, show us how it works. And the guy said, you're joking. I'm not going to show how it works. Then you're going to just take my idea. And they said, no. And he said, well, it's not quite finished yet, but I can build a prototype, but I need money. So how much? Oh, well, this is very sophisticated. I'm going to need I don't know how much it was, 1 million francs, whatever, $1 million, whatever. It was significant. So should we give him the money? Well, why not? It's a little startup. So they give the money. And the deal is he gets money for the prototype, and then if it works, they'll give him a whole bunch more money to get the patent rights and the like, because this is going to be amazing. And he's promising you can put it in a plane, fly it over an area, and it will detect the oil fields. So he gets the money, and he's building, and then he's ready for the D-Day. And sure enough, his people come along, and they put the plane on this plane. They put this black box because they're not allowed to see inside it, and then they fly a circuitous route, and they monitor what this thing says. And sure enough, every time it goes over an oil field, the light comes on and the bell goes off, and it goes, oil! And every time they fly off an oil field, the bell goes off and the light goes off and it says nothing. It's perfect. And they come back and they're like, this is amazing. And they can't find the guy. The guy has done a bonk. And they take the box apart, and what he's got, basically, very sophisticated. He's got like one of the earliest like GPS systems, okay? And he has a computer. And of course, how do you know if you've flown over an oil field? Because you know the oil field is there. So he'd programmed into it the boundary of all the oil fields. So that it would say, oh, I'm here. Oh, there's an oil field there. Let's shine the light. So there was this massive hunt for the guy. They eventually found him. And basically his defense was, oh, it didn't work. You paid me for a prototype. I built a prototype. I mean, you know, do you really want this to go further? So they didn't actually prosecute him. They basically just, you know, no more business with you. You keep away. And he was scot-free. So my wife was just, and she told me this. My wife sometimes tells me stories. And, you know, is it true, is it not true? So I finally looked it up. And yeah, it's like in the newspapers. There was reports at the time, not that big. But it was just a bit embarrassing, you know. So watch out for that. In principle, you can check something of the features underneath, though he made out like he was smelling the oil in the air or something. It was crazy. All right, so let's do a bit of theoretical stuff. We do this actually with our physics people when they're talking about being electrostatic charges. Actually, it's very similar. Let's imagine we dig a hole through the center of the Earth. And what's going to happen? And what's going to happen is, as we dig a hole through the center of the Earth, there's less and less Earth beneath us. So there's less and less pulling us downwards. And there's more and more Earth above us, so there's actually more Earth pulling us upwards. So I expect my gravity to fall, the pull of gravity to get less as I move towards the middle of the Earth. I expect it to be zero at the middle of the Earth, and then to get stronger and stronger as I go out the other side of the Earth. So if this was me, I would, sorry, I'm losing my pen again. I would basically, sorry, I'm way out. I would basically go backwards and forwards like a mass oscillating on a spring if I could go through the middle of the Earth, backwards and forwards. If I was to draw a map of it, a diagram of it, outside was this inverse square like we've been talking about, the 1 over r squared relationship. But inside, it's a nice linear relationship. As you go halfway towards the center of the Earth, there's half the pull of gravity. 3/4 of the way to the center of the Earth, there's a quarter of the pull of gravity, and so on. Which raises an interesting issue, which is, supposing you took all the mass of the Earth and you made it into a tile, into an eggshell, and you were to puncture your way through, you would be floating anywhere inside this space. There is no pull of gravity. Well, there is, but it balances out in all directions. It's like, you are being pulled by a gravitational force, but it's been pulled evenly on all sides, so you get no net effect. And sometimes it seems a bit problematic, because here you are, and you're right close to that amount of Earth, so that surely must be pulling you really hard because it's close by. But if you imagine plotting straight lines going through, here's this mass, it's a lot further away, but there's a lot more of it. So a little bit of mass at a short distance away is balanced out by a lot of mass at a long distance away. And so it doesn't matter whether you're near one of the walls or near the middle or near the edge, you would float. So imagine this planet, which is like a steel grating, and you lift up the trapdoor, and you go inside, you close the trapdoor, and you float around inside the shell. And, you know, we've never cut the Earth in two. There's other reasons why we think it's full of stuff. But, you know, it's kind of interesting. You can create a region with, well, not gravity-less, because you are being, no net gravity, I'm going to say, because you've been pulled in all directions by having a shell, an eggshell. We say we can plot gravitational field strength above and below the surface of the Earth. The gravitational field falls off, following an inverse square law, as we move above the surface of the Earth. We knew that. The gravitational field strength falls off linearly as we move below the surface of the Earth. If there was a hollow Earth, there would be no gravitational field anywhere inside. It's net zero. There's no net gravitational field. And this seems odd, but it's true. So here we have it. Now, you know, you can balance the effects of different masses. So here I am balancing the effects of different masses by basically just relying on the fact that, you know, I'm inside a shell. I could do it to some extent by having a big mass above me and a big mass below me and balancing that. So between the Earth and the Moon, there's a balance point. You know? But I can't shield myself, and that's kind of interesting. There's no known matter which stops the Earth's gravity field or any mass's gravity field from going through. I can stop an electrostatic field easily, actually. I can stop a magnetic field by using some exotic materials. But there's no known material that will stop, which will defend us against a gravity field. If I'm near a mass and it's not symmetrical, I will be pulled towards that mass. No matter which box I'm put in, I will be pulled. And that's kind of interesting when you start trying to look at the comparison between different force fields. So we have this picture of gravity, and we look at it in different ways sometimes, and Einstein looked at it in a very unusual way. Einstein perceived the gravitational field as being a geometrical warping of four-dimensional space-time, 3 dimensions of space plus a dimension of time. He pictured a massive ball warping a waterbed. So what he imagined was, you know, you have this like plastic sheet, and you roll this thing over and you get a dimple where the plastic sheet is. Massive objects distort space-time so that a football that is thrown follows a parabolic path, because that's a straight line in that space-time. So if the Earth wasn't there, the ball would go like that forever. But the fact you put the Earth there means that that straight line in space-time is bent. So is this replacing Newton? It's extending Newton. First of all, it's a different way of looking at things. You can get the same effects by being a particle physicist and saying there's these gravitons, and you can explain it using gravitons. So in one way, it's a model, just like the gravitons are a model. Can it predict things that we see? Yes, it can. What it can do that Newton cannot do is it can predict what happens to light. And we think of light as being a massless photon particle. For various reasons. When a mass travels faster and faster and goes towards the speed of light, its inertia increases, and so you can never get to the speed of light. So there's that little bit that says, okay, photons have no mass. But they have momentum, and I thought momentum was mass times velocity, so there's some issues here. And you get the sense of you're beginning to get to the stage where physics is beginning to have different models for different circumstances. And that's okay. We don't stop teaching about Newton because Einstein came along, even though everything Newton said can be explained through Einstein's theory, and not everything that Einstein said could be explained through Newton's theory. So Einstein's theory is more complete, but it's not needed most of the time. So why learn something that's really complicated when there's no need? So that's the trick of education, really, to decide when do you need this complexity and kind of feed it to you in little bits. And I don't know how you feel about that. I don't know if you've got to the stage yet where you've been fed something and then told that's not really true. And I remember it was about your level when that started to happen to me, where I started to find out that what they told me in my high school textbook was, well, it was a simplification, but I'd been a pure, pedantic student, took what I'd read as been the absolute truth, and if anything got changed, I felt cheated. And it caused a bit of a dilemma for me. I started mistrusting everything. Didn't believe anything that anybody told me, which is, again, it's not very helpful. So it's good to see the big picture and just realize the fact that we use models that work because they work, and we don't necessarily take them as being literal. So when my professor walked in during my second year as a student and said, "You'd be amazed at how many people still believe in electrons," and I went into a panic, because I still believed in electrons. And had I been asleep during that section, had he proved in the last lecture that there were no such thing as electrons? Had my high school teacher misled me yet again? And all he was trying to do was get across the fact that an electron is a model, and we can visualize it in different ways at different times. And, let's use the model that's most useful and not get worried about it if we have a better model or a more specific model and the like. So there's that realization, which I think comes with, it's like the difference between, so I watched hockey on the TV for the first time in probably 10 years on Saturday night, and I didn't have a clue what was going on. And the guys were trying to explain the rules to me, and it was like pointless. And then they started talking between themselves. And then I started asking questions like, can you see when one team is just performing better because of the way they play? Or is it just, it happens to go in the goal and they're ahead? And they were going, absolutely not. If you play this game, you can see what they're doing. And you can see the other team adjust to counter, So it's a sophisticated way of viewing the hockey. And I didn't have it, because I've never done it. I didn't spend any time, don't have much interest. And I said, a bit like that with science. There's a simple view, and that's your foundation. And as you spend more time with science, you'll get more sophisticated views of science. And to a novice, it will seem like magic, or it'll seem strange that you have these sophisticated views. But for you, it'll be useful things, different things at different times. You'll see the subtleties, and you'll say, I don't need that subtlety now. I just need this bit, So that's the game we play. Black holes. Also, honest truth. First time I read Einstein's theories, I didn't believe any of them. I thought it was total hogwash, because it was so revolutionary. And I kept trying to prove it wrong. Here's me, like a second-year physics student, trying to prove, Albert Einstein wrong. And then after a while, I realized I couldn't prove it wrong, and I started looking, and the evidence is there. Even though it seems amazing, the evidence is there. Light is bent by the sun. The evidence is there. And he predicted how much it would be bent, and it's an observable effect. You can't see it with your naked eye, but you can do the experiment. Time slows down when you send a clock around the Earth. It's been tested so many times. It's fact. And yet for me, I found it quite staggering, because I had a literal interpretation of what I was told rather than a model interpretation of what I was told. I also struggled with this, black hole. And partly because by this stage I'd got so cynical, it was like, oh, come on. You're just making this up. Here's the issue. If I dig a hole through the center of the Earth, there's more stuff on the outside of me than there is on the inside of me, and so I tend to get pulled backwards. Agreed? So there's a certain maximum gravitational field strength, which is basically on the surface of the Earth. That's the maximum field strength. But supposing, now remember, the force is equal to G m1 m2 over r squared. There's me. There's the mass of the Earth. Suppose I could take that same mass and reduce the R. So I take that Earth. Oh, I am going on. Better be careful. Suppose I take that Earth and I don't make it less massive. I just make it smaller and smaller and smaller. So it's like this, the same mass in that region. On the surface, where I am, if I don't move, I don't notice any change. But if I go inside, I feel a massive force. Let's remember that diagram. That diagram that I drew looked like that for inside and that for outside. And as I went inside, as I punctured the Earth, my force of gravity got less. But if I can take that same mass and make it smaller, then this thing just goes on like that and that and that. So here I have massive gravitational pulls. Whereas here it's the same old, because it's just the same distance away from the same amount of mass. So if the sun turns into a black hole, it will not, because it's not massive enough. But if it were to turn into a black hole, it would not actually affect the pull of gravity on the Earth. And it would not affect the pull of gravity on Mercury. But if you wandered into that space that used to be covered by the Earth, by the sun, but is now available to you, you would fall into a black hole. And once that collapse begins, it gets so strong that you no longer have atoms. You have basically not even neutrons. You go to basically a black hole, which is a singularity in space. Even the neutrons can't stay apart. And it's just frightening. And you go, this can never possibly occur. And then, lo and behold, you look into space and you see them all over the place. They are so many black holes, it's embarrassing. Okay? They're like all over the place, because the universe is a very interesting thing. Let's have a look. I've got those two. I'm gonna have to stop, and I'm going to come back next time, and we'll do a third little bit. I'm sorry about that. We'll stop here.